Okay, so yeah, thanks also to the organizers for this invitation. I'm very happy to have the opportunity to talk during this workshop. So basically, my talk will be indeed focused on forest and forest as a tool for climate mitigation. And in particular, the main idea of the talk would be to show how it's potentially possible to include both mitigation aspects of carbon and biogeophysical aspects in order to evaluate what I call the overall climatic value of forest. So, as I said, I will focus on forests and in particular forestation. So when I will talk about forestation, I basically mean either afforestation or reforestation. So it's a term that encompasses both. And so why focusing particularly on these strategies? So there are, of course, as we have seen already in the previous talks, so there are a lot of strategies that are relevant for mitigation. But obviously this one is quite important, in particular because the benefits or the mitigation potential of this strategy is potentially very high, and that's what we see here from the land report from the IPCC from last year, where we see different strategies for carbon dioxide removal, so land-based mitigation options. And we see that here on top, afforestation, reforestation is one of the two leading strategies in terms of mitigation potential, with a range that goes up to around 10 gigaton of CO2 equivalent per year or even more. And that places basically forestation among these two leading strategies together with BECCS, with bioenergy, carbon capture and storage. So for this reason, there is obviously quite a large interest on these two strategies, and in particular on afforestation and reforestation. Basically, so if we look at the Paris Agreement and the goals of the Paris Agreement, in fact, it might even be that forestation is not even an option, but we have to have some, at least some amount of forestation to be able to achieve the goals of the Paris Agreement, in particular limiting temperature to increase to 2 degrees or less. And this is what you see here. So these are projections from integrated assessment models. And this is particularly so this is a scenario that actually is compatible with 2-degree warming at the end of the century. And you see here the implication for land use of this scenario. And in particular here, you see the increase in forest area and the increase in the area of bioenergy. And so this increase that we see here, just to give an idea of the order of magnitude. So roughly what we are talking about here at the end of the century for the forest change that we have it's roughly 2 times the size of India. So that's the median of this integrated assessment model. So we are talking about having 2 times the size of India of reforestation or afforestation. So it's quite substantial, and in fact, it's not even. I mean, it's just the median. You see that some IAMs are actually going even higher than this. Some less. Some have less reforestation because they also have compensation through bioenergy and BECCS. But overall, it's just, so it's not to say that the goal is to have 2 times the size of India covered by forests. It's just to illustrate the order of magnitude of what we might need to do to achieve the Paris Agreement goals, if we believe these integrated assessment models. And just to give another element of context, so the bond challenge is basically, the objective of the bond challenge is to restore 3.5 million square kilometers of forest by 2030. And that would be roughly in the middle here. So that would be roughly the size of India, and in fact, a bit more than that. Again, indicating that that reforestation and afforestation is seen as a main element of mitigation globally. Now, because this involves, as we see here, very substantial amount of land that we need to find to actually implement this scenario. This comes, of course, with a number of challenges. which are listed here. So the first, of course, is that there are uncertainty in the mitigation potential of these approaches itself, and we saw that from the previous figure I showed. There is about 1 order of magnitude variation in the different estimate of the mitigation potential from reforestation, so it's still very uncertain. And as was mentioned also already before, the carbon storage that would be induced by this reforestation is not even guaranteed. So there is also a risk of non-permanency of this carbon storage in the face of climate change and increase in extreme events and various disturbances, including fire. Another challenge is, of course, that there will be trade-offs with other objectives. So given the size of this large-scale forestation that is needed, there will be obvious trade-offs between objectives such as conserving biodiversity and maintaining food security, which are also a source of concerns. And finally, and that's mainly the goal of this workshop and of my presentation, there are challenges related to biogeophysical effects, in particular albedo, and the fact that albedo change could potentially limit the applicability of such large-scale implementation. And we have heard a bit already about this before, but this is just to illustrate one example of a study with a global climate model where we looked at the difference between forest and grass. And what we see here, we can start from this plot. In blue, the blue bars are basically the temperature change that would result from albedo change by converting forest to grass. So if you reverse the sign, this is giving you actually the signal of forestation. So forestation would mean an increase in temperature due to the lower albedo of forest. And this increase in temperature is not homogeneous. So you see that it's lower in the tropics, but it's increasing at high latitude due to the snow albedo effect. So basically, one of the other questions of this workshop was, could albedo offset mitigation, the effect of mitigation practices? And in the case of forestation, the answer here is clearly yes. So we see that at least partly this is an issue, because at all latitudes, we do have a warming effect from forestation according to these models, but it's confirmed also from other sources of evidence. So that's one aspect, but of course it's more complex than this, because as you see, it's not only albedo. Albedo does not happen alone, but there are also other processes that will be modified by forestation, in particular evapotranspiration and surface roughness. And these processes, the effect of these processes is actually to counteract the albedo effect in a way that if you reforest, you would actually cool temperature, you will decrease temperature through these effects. And it's important because, for instance, in the tropics, these what I call non-relative effects would actually dominate over the albedo effects, which results in a different signal in the tropics. The forest is cooler than open land in the tropics, whereas the albedo effect dominates at high latitude. So basically, this is showing that yes, albedo potentially can offset some of these benefits from mitigation through forestation, but there are other processes that are very important here, and the net effect depends on the balance between these processes. So based on this, what the question we are asking is that obviously it's important to consider the overall climatic value of forests, so not just carbon, also not just albedo, but the sum of these processes, so including biogeochemical effects, which I call BGC, and biogeophysical effect, BGP. And if we want to do this, the central question then is how to factor in these biogeophysical effects when we evaluate the climate mitigation potential of forestation, which is of course a central question of the workshop itself. And if we can do this, then the next question is, what does it tell us about the priority areas for forestation and of course also for forest conservation? So that's the question that this person here, Michael Windisch, has tackled in in his master thesis, and he's actually with us now. So since we don't see each other, I include his picture here. So what Michael has been doing in this work is that he has used a purely data-driven approach to quantify this combined effect of BGC and BGP impact of forestation. And data-driven meaning, so we are trying to rely the least possible on models here, but really to use as much observation-based data as possible. And then fundamentally, the essential element in this work was to come up with a metric to combine these two effects, because that's the main challenge, and Ryan has talked a lot about this already. But unlike what Ryan presented, what we have been using is not based on relative forcing, but it's rather based on using a carbon equivalence through the transient climate response to cumulative emissions. And I will show later a bit more about what this means. So that's the central concept here, to compare these two effects. And the last aspect is that we took, let's say, a scenario agnostic approach, in the sense that we are not assuming any forestation scenario in the beginning. So that's what you would say if you use a climate model, you would need to start with some assumption about what is the forestation scenario you are trying to assess. But here we are not doing that. We are just looking at every possible site on Earth where it is theoretically possible to put forest. And then we are trying to come up with a kind of ranking of these different sites, where it is best to actually put these new forests if we have to put them somewhere, rather than predefining an objective in terms of scale of reforestation. Then more specifically, so the methodology to do that is the following. So the starting point is first to look at the land cover map. So we took GLC 2000. And for the forestation approach, what we are considering here is what are the let's say the pixels on Earth, the sites on Earth which are not forested now currently in this map, so which are under grass, shrubs, or crops. And then we will assume that this can be converted to a forest, and the forest it will be converted to is actually, so the assumption we take is that it will be converted to the closest forest we find within a window of a quarter degree resolution within around this pixel. So basically that defines what type of conversion we can have and where this is occurring. And then from that, the next step is to calculate the effect, both in terms of the carbon effect and the BGP effect. So for carbon, the way Michael has been doing that is he took the IPCC Tier 1 carbon density map for the biomass, and then looking within this window of quarter degree, trying to find what is the closest forest that is in this window, and then the difference between the biomass in this forest and the non-forested patch is basically the potential that we find that we have in terms of carbon storage potential. Of course, it means that we are limited here by the data availability. So if we have a region where we do not have any forest now, we actually don't have any value. So that's the only constraint in this approach compared to a climate model, is that we are constrained by the availability of the data and where we find this land cover. So we also consider soil organic carbon, based on a publication that is giving the relative change in soil carbon for different types of land conversions. So we also included that to calculate the overall BGC effect. And in parallel, we calculate the biogeophysical effect on surface temperature. So it's really the metric here that we consider is not carbon, of course, it's surface temperature. And this was done using two data sets. The one from Ryan Bright, which is a data set looking at temperature change due to various land conversions globally. So basically it's giving us like potential sensitivity, local sensitivity in terms of temperature of doing a given conversion. And the Duvillé data set, so I think that Greg Duvillé is also here today, is another data set that is that is also doing the same thing, but from an independent method, which is relying on satellite remote sensing, whereas the method from Orion is relying primarily on FluxNet measurements. So now that we have this, so we have estimated the BGC effect and the BGP effect, but of course the obvious issue here is that we have different units. So we have the carbon storage on one hand, and we have the surface temperature effect from the BGP effect. So we need to find a way to convert the two. And the way we do it is not using, as I said before, the radiative forcing approach, but rather to try to convert temperature into a CO2 equivalent by using the transient climate response to cumulative emission. So what this means, this transient response to emission, is that it's basically the relation between temperature change and cumulative emissions of CO2. It's based on CMIP 5, so it's from models that we get this. And it gives a direct relation to convert from temperature to emission, basically. So we basically divide the temperature change that we obtain from these data sets by this transient climate response. And then what we do also additionally is that we divide by the global area of the Earth. We do that because the change we are considering is a local change. And that's actually very similar to the method Ryan presented before for the radiative forcing, where we also divide by the global area. So that in the end, we get what we get is a CO2 equivalent measure of this BGP effect at the local scale. So we can then compare pixel to pixel based on this measure. And ultimately, then of course we can accumulate or we can sum these two effects to get what I call the climatic value of forests, which includes both the BGC and the BGP effect. And so the process I was showing was for forestation, and as I said, we also looked at forest conservation, so the avoided emission that we would have by conserving forests. And here, so it's the same methodology everywhere, except that we start from the different hypotheses here. So we look at the land cover map, we look at where there are existing forests now, and then we compare the biomass or the temperature effect in this existing forest compared to agricultural land, which basically give us then the emission, the avoided emission from conserving this forest. Now going to the results, this is what we find in terms of this cumulative effect of BGP and BGC effect. So that's the climatic value of forest considering both in CO2 equivalent per hectare. And on this side, you have the effect of forestation. So as you see here, the pixels that are highlighted are the one that, at least from the map, the land cover map we used, are considered to be free for reforestation or afforestation. Which, by the way, is something I forgot to mention. But so we are not restricting ourselves to forest restoration. So we also include afforestation and so as well as reforestation. So that's the results for forestation, where you see that you tend to have higher values of this indicator in tropical regions, also in some regions around the US and Europe. And these values are decreasing toward the north because here basically the biogeophysical effect starts to dominate, in particular due to the albedo issue that we talked about. For forest conservation, the map is showing here. So what you see that the regions that are highlighted are regions where there is forest today. And what we are quantifying here is what would be what is the climatic value of this forest compared to agricultural land, or in other words, what we would lose in terms of CO2 equivalent if we would remove this forest. So interesting is to see that you see that much higher values. So the much higher values that we get in this forest conservation map compared to the forestation maps indicates that basically there is more to lose from removing existing forests than to gain from reforesting or afforesting. The reason is that because we have a lot of carbon, so the carbon density in these tropical forests is very high, and this makes this forest very climatically very valuable compared to what we could gain from reforesting other areas. So now starting from this, what we can do in addition to that is that we can also compare the relative strength of these two effects, the BGP effect and so that's basically the BGP divided by the BGC effect. And you see that for forestation, so we have a lot of values around 20%, so meaning that albedo and these other biogeophysical effects are representing around 20% of the effect compared to the carbon effect. So it's quite substantial, and it's basically a confirmation that it's important to actually account for these effects. And for forest conservation, you see that typically there are a bit lower values for this diagnostic, which indicates that in this remaining forest, the carbon effect dominates a bit more. Again, in particular in these tropical forests, which have very high carbon density, there is so much to lose in terms of carbon that actually the biogeophysical effect is not so important or less important than for the reforestation, the forestation scenario. Well, which also is interesting because it tells us that maybe for when we are looking at priority areas for conservation, it's maybe okay to consider only carbon. At least it's better than for forestation, where clearly it's important to take into account both. Now, just to show an example of how this can be used, this kind of map, so to basically prioritize conservation areas or forestation areas. So this is again for forestation and here for conservation. So basically that's the distribution of the sites that we have. So that's their frequency ranked according to the climatic value, which combine both effects. And of course, what you want is to have a lot here because it means you have a lot of very high value potential forests that you could plant. But as you see, it's not really the case for forestation. There is actually very little high value forests, and there are a lot of forests which are actually rather low value. Again, if we look at conservation distribution here, it's the opposite. So you have a lot of areas which are mostly in tropical areas which have high value according to this metric, and which again points to the fact that we have much more to lose by not conserving the forest than to gain by reforestation because of this skewed distribution of the climatic value. This is here highlighting the bond challenge. So again, what I mentioned at the beginning, the 3.5 million kilometers square of forest. So if we want to implement the bond challenge, this would mean to basically tap into all these forest areas here, all these forest sites, assuming we are starting from the highest climatic values and going down. And indeed, so you see that we need to tap into quite some not so high value forest to achieve this target in terms of area. So these were the main highlights from the results. So now I want just to highlight some caveats of this approach. So one caveat is that we are ignoring non-local effects. So because we are looking only at the present day difference between non-cover types as the metric to evaluate the effect of future forestation or conservation. So we are not considering any non-local effects in this approach. And of course, this is something that is much easier to do with climate models than this kind of data-driven approaches. Ryan mentioned already this problem here, so I won't go into that. But yeah, there is basically a scale mismatch. So even though we are able to come up with a metric to compare the two, we still have to keep in mind that the scale at which these processes happen is very different. And another drawback or caveat is that we need to assume climate independence. So again, the data that we are using, they are based on present day data. But if the climate is changing in the future, just to take an example, if there is less snow in the north, then typically this albedo effect will be different. And this type of effect is something we are not considering in this approach. It's maybe okay because we are focusing on mitigation here, so which means we are more like in the hypothesis of low emission scenario where climate change is actually lower, but it's still an issue to have in mind. Another potential issue is that we are not considering changes in forest types or species. So we are, as I said, we are just assuming that we would replace by the closest forest nearby without doing any changes to the forest composition, but that could be actually an important aspect. And finally, this climatic value of forests, as we have it here, is very temperature centric. So it's based on the effect on temperature, but there is actually more than this. There are effects, for instance, also on precipitations from forestation, which would be important to take into account. So in the rest of the presentation, I would like just to expand a bit more on these two last topics, so the effect of tree types and the effect of precipitation other than temperature. So starting here with the effect of tree types. So here the idea was to look at whether broadleaf trees would be more valuable than needleleaf trees in terms of albedo and climatic value, but we didn't consider carbon for this study. Sorry, I forgot to mention that's the work from a postdoc at ETH Zurich, Jonas Schwab. I don't think he's here today. So what we did, so what Jonas did is that we analyzed all this data of albedo across Europe, and then looked at the difference between broadleaf and needleleaf trees. And the difference here is very clear. So we see positive values everywhere. So that's the difference of broadleaf minus needleleaf trees. And we see that broadleaf trees have actually higher albedo than needleleaf trees across different Europe. So of course there are regional variations and also seasonal, but there is a very systematic signal. We can see it here even from this picture. So these are conifers and these are broadleaf trees. And you see that even visually, you see clearly this difference. So now, of course, this you can imagine that this will affect temperature as well. And then the next step in this analysis was to use a statistical model based on generalized additive models and to look at land surface temperature from satellite and then build a model that would predict the temperature of the broadleaf versus the needleleaf trees using different inputs, in particular land cover, but also all other inputs that would be relevant in order to be able to disentangle the effect of confounding factors. And the result is here. So that's again the difference of broadleaf minus needleleaf in terms of temperature. And we see that we have everywhere, so colder temperature over needleleaf trees. So needleleaf trees helps to keep temperature cooler in the direct, so directly where they are. And this effect, and it's maybe more interesting, is actually increasing with the background temperature. So when it's very hot, it's actually when this cooling effect is the most is largest, which is very interesting for the resilience of forest itself, because it means that this kind of forest could be more resilient if they include a certain proportion of broadleaf trees. The last point I wanted to illustrate is the effect of forestation on precipitation, because as I said before, we are still very much temperature centric when we looked at this land cover change impacts. And in fact, there might be some effects also on other variables of interest, and in particular precipitation. This is work from Ronnie Meyer, a PhD student at ETH. So he looked at precipitation data so rain gauges measurement, and he paired these sites across Europe to compare sites dominated by forests and sites dominated by agricultural land. And this analysis is showing that if you compare all this, if you do the comparison between these pairs and then aggregate the data across Europe, there is actually systematically more rain over forest compared to agricultural land. So it's raining more over forest. That's what the data is showing. So in the next step, that's what we see in red. Then Ronnie built again a model, statistical model based on GAMS, on generalized additive model, to be able to predict temperature at these sites. And the model, as we see here, is able to predict indeed this temperature difference. And the nice thing with having this model is that then it can be extrapolated to the future as well. And that's what is done here. So here we consider, based on this statistical model, a forestation scenario. It's a forestation scenario based on the Griscom et al. Map of reforestation. And you see what this would mean in terms of temperature change based on this data-driven approach. And it would actually imply an increase in precipitation, mostly in Southern Europe. And what is interesting is that climate models predict that precisely in Southern Europe, there will be a decrease in precipitation in summer in any scenarios, but you see one example. And that's interesting because we see that this forestation effect has a potential, at least partly, to mitigate this precipitation decrease. So again, that's something that comes in addition to the mitigation potential that could be very relevant to consider when planning forestation activities. And I come to my conclusion. So what I wanted to show is that albedo change definitely can be a trade-off, and it's the case as I've shown for forestation. In other cases, in other example of practices, it can be a co-benefits, and we have heard already a few examples. So I've showed the example of broadleaf trees versus needleleaf trees. Sonia showed a study we have done on no-till farming. And tomorrow, I think we will have also some other presentation on cover crops highlighting this type of co-benefits. So basically, albedo can be both. But also albedo change does not happen alone. So there are changes in evapotranspiration that are very important to take into account because the net biogeophysical effect can be sometimes even dominated by these other effects. And finally, last word would be that the implementation of mitigation policies should not consider, should consider obviously all these effects I mentioned, but even beyond surface temperature should also consider, for instance, changes in precipitations. And this is of course more challenging because it's more difficult to design a metric that would encompass all these aspects. So it's maybe more complex, but it's important to also keep that in mind.